The whole reason we do limiting reactant calculations is so that we can figure out how many grams of each product will be formed. You need to use the limiting reagent. Otherwise, you'll get an answer that violates the law of conservation of mass. So first you need to figure out what your limiting reagent is. You can start with the given amount of either. If I start with 50 grams of aluminum, I can determine the amount of Fe2O3 needed. First, I convert grams of aluminum to moles of aluminum by dividing by the molar mass. Grams cancels. Then, I convert moles of aluminum to moles of Fe2O3 using the mole ratio. Moles of aluminum cancels. Finally, I convert moles of Fe2O3 to grams of Fe2O3 using the molar mass of Fe2O3, and moles of Fe2O3 cancels. And I see that I need 148 grams of Fe2O3. Comparing that with what I have, which the given says is 50 grams, I can see what I need is more than I have. Therefore, Fe2O3 is the limiting reagent. That means that my stoichiometric calculations all start with Fe2O3. To determine grams of Fe formed, I start out with my 50 grams of Fe2O3. I use the molar mass of Fe2O3 to convert it to moles of Fe2O3. I use a mole ratio to convert to moles of Fe, and then I use another molar mass to get to grams of Fe. Here's what it looks like. I take my 50 grams of Fe2O3 and I divide by the molar mass of Fe2O3. This makes grams of Fe2O3 cancel. Next, I multiply by the mole ratio. This comes from the balanced equation, see above. Moles of Fe2O3 cancel, and we're left with moles of Fe. Then I multiply by the molar mass of iron, which is 55.85 grams per mole of iron. Moles of iron goes away, and we're left with grams of iron. And according to my calculations, we get 35.0 grams of Fe formed. To find the grams of Al2O3, we're going to do a similar calculation. We'll start with our grams of Fe2O3. We'll convert it to moles of Fe2O3 just as we did above. Then we'll use another mole ratio to convert to moles of Al2O3. And then we'll go to grams of Al2O3 using a molar mass. Let's see what it actually looks like. My first conversion is dividing by the molar mass of Fe2O3. Grams of Fe2O3 goes away. Now I've got moles of Fe2O3, which I can convert to moles of Al2O3 using the mole ratio from the balanced equation. And then I had to calculate the molar mass of Al2O3, I should say Al2O3, which is 101.96. So, moles of Al2O3 goes away, and we're left with grams of Al2O3. And I see that I'm going to form 31.9 grams of Al2O3. So, the iron 3 oxide was limiting. All of the Fe2O3 was used up. But aluminum was our excess, so there should be some aluminum remaining. Now, there's a quick way to calculate this, where you can use the law of conservation of mass, LOCOM. This says that the mass of the reactants equals the mass of products. We just calculated the mass of products. Namely, there was 31.9 grams of Al2O3 and 35.0 grams of Fe. So 31.9 plus 35, that gives us 66.9 grams total. Now, the mass of reactants, that's the 50 grams of Fe2O3 plus X grams of aluminum. So if we subtract 50 from 66.9, that gives 16.9 grams of aluminum was used. And then how much is left over? Well, we started out with 50 grams of aluminum minus 16.9 grams of aluminum. That's 33.1 grams of aluminum excess, unreacted. Now, using the law of conservation of mass as a shortcut, you could also determine the amount excess by stoichiometry. You could go from grams of Fe2O3, your limiting reagent, to moles of Al, to grams of Al. That'll determine the grams of Al used, and then you can subtract that from 50, and you'll get the excess. You should get the same answer.